السلام عليكم. أنا تامر عصام، مدرس بقسم الرياضيات والفيزياء الهندسية جامعة اسكندرية. إن شاء الله I'm going now to present a brief presentation about my research work in the project entitled Queuing Models for Time Critical Systems. The outline of presentation can be divided as follows: introduction about time critical systems, the deployed methodology, the research findings, open research directions, and finally the benefits about participation in the project. First of all, the IoT of time critical systems, such as smart manufacturing system or healthcare monitoring systems, can be characterized as real-time status update systems. To demonstrate the structure of such systems, let's consider an example of temperature monitoring systems. In this example, the temperature signal is detected by a temperature sensor. Status updates about the temperature signals are transmitted through the network to the interested recipient for monitoring and control purposes. In such systems, it is important to ensure that the received information should be as timely as possible, as fresh as possible, in order to ensure accurate monitoring and control decisions. However, there are two main challenges for such systems that may adversely affect the reliability of such systems. Limited network resources due to limited spectrum and limited processing capabilities, and distinct time criticality between applications. Actually, there are applications with higher time criticality, such as autonomous vehicular networks, and others with lower time criticality, such as smart homes. Accordingly, it is important to design appropriate schemes for service differentiation between such applications. Accordingly, our general objective is to study IoT of time critical systems and design appropriate queuing models and packet management schemes that enhance the reliability of systems. To fulfill this objective, we deploy the following methodology. First, we conduct a literature survey about IoT of time critical systems from different perspectives. For the source nature, we have a single source system, multiple sources without priority, and multiple sources with distinct priorities. And such a setting is highly motivated in real-life applications. Actually, in real-life applications, we have different applications, and each of them has time-critical constraints. For the system nature, we have lossless systems where all status updates should be transmitted to the monitor for prediction and estimation purposes, and the lossy systems where part of status updates may be dropped during transmission to mitigate information backlogging عشان اقلل التكدس اللي ممكن يحصل في الانفورميشن في الشانل بتاعتي. For the performance metric, we have traditional metrics, system delay and system throughput, and a new metric called the age of information, which quantify information freshness. This metric is important in IoT of time critical systems because it represents to what extent the information at the monitor is updated according to the information at the transmitter. So by enhancing this metric, we can ensure the reliability of our systems. According to the literature survey, the research gaps can be identified as follows. We found a limited study of the age of information metric in IoT of time critical systems, and we found a limited consideration of priority-aware IoT networks, despite being highly motivated in real-life applications. Finally, the existing schemes for priority-aware IoT networks don't ensure even satisfaction between classes, and they cannot be controlled to accommodate any variations in traffic conditions. Accordingly, the research objectives can be outlined as follows. We study priority-aware IoT systems for lossy and lossless systems. We propose new packet management schemes that mitigate the drawbacks of the existing one. We analyze the stochastic behavior of age of information, and we optimize the age of information to fulfill the optimal network satisfaction. For the analytical approach, we analyze the age of information using a stochastic hybrid system. Actually, this system is most commonly used to analyze systems whose state is a hybrid of discrete and continuous components. We have discrete and continuous components that represent the system state. In our case, the discrete components represent system occupancy, and the continuous component represents age of information. The stochastic hybrid system mainly depends on Markov chain continuous time Markov chain analysis and linear algebra in order to provide some stochastic behaviors of age of information. For our research findings, in lossy IoT systems, we propose probabilistic hyperdiscipline and interruption-based hyperdiscipline. This work was published before the start of the project, so it acted as a preliminary for our project. During the project, we propose elapsed time-based hyperdiscipline and energy-based hyperdisciplines, and this work was published in 2 IEEE conference papers and 1 IEEE journal paper. For lossless IoT systems, we propose probabilistic hyperdiscipline and equivalence hyperdiscipline, but this work is still under progress. For open research directions, I suggest some extensions considering multiple heterogeneous servers connected in series or parallel structure, motivated by multi-hub networks and multi-tier mobile edge computing networks. Actually, in our work, we only consider one server, so this extension is important for future consideration. Second, considering general service time distribution to align with real-life scenarios. Finally, the benefits of our participation in projects from my perspective can be outlined as follows. Completing my PhD thesis, publishing highly impacted journal and conference papers, the financial support for attending international conference. I actually attended the ICT 2025 conference that was held in Montenegro in April 2025. Finally, the follow-ups support research consistency alongside teaching responsibilities. Thank you.